Well, good afternoon. It is Thursday, March 11th here in Advanced Level Chemistry at Spain Park. Today we're going to kind of go over all of the equations here that we did on e-learning on Tuesday. We're going to continue to practice our total and net ionic equations because based upon what I just saw on this assignment that you did on these last two, we still need a lot of work on total and net ionic equations. Okay? Today's the day to ask questions. Today's the day to try to make sure there's no new material. We're just going to kind of review. Now, going to have a quiz tomorrow, just over like 5 equations and 1 total and net. Just see, practicing balancing and writing the equations, kind of like this. 5 of these, identifying the type of reaction, being able to complete it and balance it, and then 1 total and net ionic equation like at the bottom. Okay? So it should only be like a 15-20 minute quiz. But I need to know where you are. So then we're going to go in and we're going to actually start in on a new unit today. Okay? But it's going to be a fun one. A fun start, I should say, to stoichiometry. Okay? We're going to do some more chemistry. And then the big test will be over both equations and stoichiometry. Okay, just for the sake of time, we're so far behind. All right, so when I'm looking at Be plus O2, first off, what type of reaction does that have to be?
Composition.
Because it's only an element and element. They can't swap, they can't replace, they can't do anything. The only thing they can do is combine. So it's a composition. Now, a lot of the other teachers are calling this synthesis. It's the exact same thing, just, they're synonymous. All right, so that's going to make Be, do I just say BeO2?
No.
How do I determine what the subscripts are? The charges. You balance the charges first, balance atoms last. Okay? So Be is an alkaline earth metal, group 2, so what's its charge? Plus 2. We'll say 2 plus. Oxygen, we just know, is always 2 minus, so we don't need to do anything. So now my charges are balanced. Now I have to balance atoms. So I have 2, so I need a 2, but that gives me 2, so I put a 2. Okay? Now, what's the second type of reaction? Number 2. How do I know, tell me, how do you know that that's single replacement?
There's 2. There's like compound and a single.
That's right, it's an element plus a compound. Right? That's how you know. So now which one is going to get replaced, the lead or the nitrate? The lead. Because iron, even though it's 0 here, iron, every element in its natural state is 0, it tends to form positive. All the metals want to form positive. So a metal is not going to combine with a metal and make FePb. This is want to go with the negative nitrate. And so we're going to end up having, now you have choices. Because iron can have more than 1 possible oxidation state. Okay? So it can be plus 2, plus 3, or plus 6. What's the bold one on the periodic table? Plus 3. So let's pick that one. Okay? If you pick 2, that's fine. It won't change that much. But if it's 3 plus, nitrate is NO3 minus, what do I need to do?
We've got to
And then what's left over is just Pb. And that's going to be just a solid. It's going to be 0. It's not going to have a charge on it. Okay? When we get to go practicing total and net ionic equations, we'll come back and look. And the whole reaction really is just lead stealing 2 electrons or 3 electrons from iron and becoming 0 while iron loses the electron, becomes an ion. Now, is this balanced?
Yeah, put 2.
I see a 2 and a 3. So I need to put a 3 here and a 2 there, right?
And that's 3 on the PV.
Now that gives me 3 PBs, so I need 3 PBs, but it gives me 2 FEs, 2 FEs.
So if we use the 2 for the
If you
iron,
use the 2, you don't have any coefficients. Right?
we could have used 2.
If you use 2, yeah, I mean 2 is a possibility, so that would have been 100% right. Could have used 6. It's pretty rare, but you could have used 6. All right, what type of reaction is, oh, so this was single replacement. What type of reaction is this one, and how do I know? Decomposition, because
Just
there's only one thing. So there's nothing for it to swap with or rearrange or whatever. So we know that this has to be decomposition. And what's the name of this ion? Chlorate. So it's a metallic chlorate. Now again, you're going to have on the decomposition rules, you'll have those rules that say metallic chlorates, when heated, decompose into metallic chlorides plus oxygen. So what's the metallic chloride going to be? MgCl, but magnesium's what charge?
+2
And chlorine is?
-1.
So what's the formula going to be?
MgCl2.
MgCl2 plus magnesium, metallic chloride plus oxygen, O2. And it's going to be oxygen gas. Now, there's no mention of water, just for states purposes. That would be a solid, and that's a solid. Now, you're not going to have to worry about states unless like on the other side of this sheet at the top, I give you all the words where it says a solution of this is mixed with a solution of that to make it solid, you know, then it's telling you the states, and you just represent it with solid, liquid, gas, aqueous. But just looking at it, you're not going to be expected to know what the states are. Okay, so don't stress about that. I just kind of start putting stuff up there. I'm just kind of throwing it out there, you know, just to kind of plant seeds. All right, now this one is unique because barium is what charge? +2, right? But this is an O2, which we know the total has to be that. So what's the charge on each oxygen? -1, not -2. It's an O2 with a -2 charge. What do we call that?
Peroxide.
That's a peroxide. Okay? O2 with a -2 charge. So this is a peroxide. It's barium peroxide.
Don't make me mad the other day, I couldn't figure it out.
Did you look it up and then it just...
No, I just couldn't find my sheet,
Oh.
and then I found it.
Well, it's important to keep your sheets together. So, what's that? What do peroxides decompose into?
Metallic oxide and oxygen.
The normal oxide, which will be barium oxide, so then it'll be Ba2 plus and O2 minus plus oxygen gas. Oh, by the way, we didn't balance the one above it. How come you guys let me go without balancing it? How do I balance this one?
Put 3 in there.
I need a 3 over here. Okay? So now I have to balance this one. 1 barium, 2 oxygens, but I have 3. So I got to put a 2 here to make it have 4 and a 2 there. So peroxides are hard to recognize. You just got to pay attention. So just know on a decomposition with that peroxide. Now, with the single replacement reaction, how do we know if a reaction is going to occur or not?
If the metal is more active.
If metal has to be more active, iron has to be more active than lead, copper has to be more active than hydrogen. Everybody open your book to the activity series. Does anyone remember what page it was on?
278.
270 what?
8.
278. Oh, you made a copy?
Maybe.
Page 278. Now, you will be given a copy of this. Okay? And when you look at copper and hydrogen, is copper more active than hydrogen? Is it above hydrogen on that activity series?
No.
No. So what does that mean?
There's no reaction.
No reaction. You put a penny into acid and nothing's going to happen. Now, I may do this one, we'll just see, maybe during lunch today. If you take a new penny is not pure copper anymore. A new penny is copper with zinc on the inside. Is zinc more active than hydrogen? So if you scratch it and scratch some of the copper off the surface and let the acid get to the zinc, it'll dissolve the inside of the penny.
Sean?
Yes.
Is Peyton Vincent in your
Say the name again.
Peyton Vincent.
Who did they say?
Peyton Vincent.
Peyton. Oh, she was not in there today, no.
She did not come to AO. Okay, thank you.
I don't think.
I'm sorry, my dad doesn't know the name of this dude.
Well, AO I for sure don't, because I never talked to him. But I know all y'all's names. Okay, so what happens here?
Better know what it is.
No reaction. Okay? But what I was saying is we can take a penny, scratch it, put it into some acid, HCl, and the zinc will react and dissolve, and the copper won't, and so you end up getting just this hollow penny. But it takes a good while to do that, but we'll start that during lunch today. Okay? What type of reaction is this one going to be? Well, this would, by the way, this is a decomposition. This would be a single replacement, but it's nothing. What's this one going to be?
Composition.
Composition. So it's just going to make AGS. But how do I determine my subscripts? Charges. What's the charge on silver? +1. Now you're not going to have to, again, you're not going to just know that. You're going to go to the periodic table and you'll see that there's a little number 1 right there above the symbol. That you're going to have that periodic table always. Okay? And what's the charge going to be on sulfur? -2. So the formula is going to be Ag2S. So we're going to need a 2. Silver is a solid, sulfur is a solid. This is an ionic compound, so it too would be a solid. Ionic compounds, covalent network, and metallic are always solids if there's no mention of water. All right? What type of reaction is this one?
Double replacement.
Double replacement. Specifically, we have 3 types of double replacement. We have a precipitation reaction, we have an acid-base neutralization, and we have a gas forming. Which one do you think this one is? No,
Acid-base.
that means we only have one choice. Remember, when the positive thing is hydrogen, that makes it an acid. When the negative thing is a hydroxide, that makes it a base. So the hydrogen's going to go with the hydroxide, the potassium's going to go with the oxalate. Double replacement. So what do we get? HOH, water,
Plus K2C2O4.
Why K2?
To balance it,
Because-
C2O4 is
Minus
-2.
2.
2.
And hydrogen is +1. Or potassium is +1. Okay? Now we have to balance this how?
2 on the H2CO.
No, just,
I mean, that's what
yeah, because we had 2 Ks here, I had to put 2 here. That gave me 2 OHs. So I needed the 2 OHs. I already had the 2 hydrogen. That's why I like water as an HOH again, because it's an H plus combining with an OH minus, and you can just kind of see it. It makes it easier to balance than trying to do all the hydrogens and oxygens individually. All right, what type of reaction is this one? Single replacement, but now again, chlorine is neutral here, but is chlorine going to be attracted to the iodine in the same family or the metallic potassium? Potassium, okay, because this time we're replacing the negative thing, and these were we're replacing the positive thing. So we're going to get KCl, but we balance the charge. Just because it's a 2 here doesn't mean it's going to be a 2 over there. What's the charge on potassium? What's the charge on chlorine?
-1.
And +1 and -1, so it's just KCl. And what's left? Iodine, but because it's ion, it's I2. So we have to balance it again, putting a 2 and a 2. Are we doing all right on these?
Yes.
Wait, why would it be 2 on the side?
This iodine, because it's one of our 7 diatomic elements that we just have to know. Anything that ends in gen, Gen, or ene, ine. So when we say the fluorine, chlorine, bromine, iodine, it's supposed to be iodine, but it's in the same family. Why would we pronounce it differently?
Because it's English.
Yeah. All right. So what's this one going to be?
Combustion of a hydrocarbon.
Combustion. What's going to be an indicator? How am I going to know really that this is a combustion, a burning? The plus O2 right there. Anytime you're going plus O2, it's burning. So really, the beryllium is oxidizing, it's burning on this one too. But it's just composition. This is your hydrocarbon. What are the 2 products always?
Carbon dioxide and water.
Carbon dioxide, we know that's a gas, and water, which we know to be a liquid. Now, 3 carbons, 3 carbons, 8 hydrogens, 8 hydrogens. That gives me 6, and 4 makes 10 oxygens. Well, I already have 2 here, so I need 8 more. So what do I do? Put a 4 in front of the O2. We can just say hydrocarbon combustion, HC. We want. Did I give you a unit? Did I tell you what? Yeah.
What?
It says it right here, HC. All right, so 10 is going to be double replacement. To me, these are the easiest ones because they just swap. So you're going to get what?
Calcium nitrate.
Calcium, which is what charge, and nitrate is what charge?
Plus 2 and
Plus 2 and minus 1. So the formula is going to be,
Ca.
so we got to put a parenthesis in a 2, plus mercury, and mercury here, we can just kind of know Mercury's in the plus 2 state, the reverse crisscross. So it's going to be mercury 2 iodide, HgI2. Now, this is a double replacement. Is this going to be a precipitation, acid base, or gas forming reaction?
Precipitation.
This is going to be the precipitate. Which one would be the precipitate, do you think?
Mercury iodine.
The mercury, because all nitrates are soluble. So this would be aqueous. In order for this reaction to occur, you have to have a precipitate and mercury iodide. And then again, you could double check up here. You can see for iodide, most are soluble, but silver, lead, mercury, and thallium form precipitates. They're insoluble. So mercury is one of those 4. So that's going to be my solid. All right?
That's gonna stay up there during the test,
Yes.
right?
Yes. All right. I got to move everything up. Does anybody have any questions on 1 through 10? We're good? So we're all making 100 on the quiz tomorrow so far.
Yeah.
If we can do simple math.
All right. Going once, going twice.
So,
Gone.
This week was the, last week we were in school last year, before we got home.
yeah, that was depressing. Like last week,
Weird.
it was like last week on Thursday or Tuesday or something. It was like a year since we gotten.
Yeah, it was the 1 year anniversary.
It was so depressing because it's like, that's been a year ago.
It was March.
It's March 13th.
The
Yeah,
1
it's
year
until
anniversary is
Saturday.
in
I thought it was
2
Go
days.
for
Oh,
us.
March 8th.
No, it's Friday the 13th.
No, the 8th is when they started canceling stuff.
Yeah, for other
Yeah.
places.
Oh, well.
And
Yeah,
then
I
they got
never,
to us
ever,
days
I
later.
never, ever, ever dreamed. I thought it was so crazy that, and then it
We
just,
were all like, yeah, we're going home, and now you're.
yeah,
Yeah.
just a long spring break, but then we'll be back. No, we're not coming back. No, we're,
I know, I was in Dothan for
Oh.
softball, that's where we're
Hey,
going this
I had
weekend,
one.
so it's like throwback.
If you had a birthday during that first like 3 or 4 months of quarantine, that was sad stuff. If you wake up at home and you just be like, oh, there's cars
Yeah.
in the driveway, too bad I can't go say hey, because.
I turned 60 during quarantine. No party, Or nothing, all by myself.
I have
We're
fried,
paid for you.
I have homemade fried donuts. Some
Yeah.
good stuff.
Okay, so barium hydroxide. First off, this is gonna be what type of reaction?
Yeah, we had our.
Decomposition.
Decomposition.
Mr. Hobbs, I feel like the people at home just enjoy our off-topic conversations.
Well, you know, hey, we just gotta be real sometimes. All right, so metallic hydroxides, when heated, decompose into the metallic oxide and water. So what's the metallic oxide gonna be? Barium oxide plus 2 minus 2, so it's just BaO plus water. And the good thing about those is they're already balanced. So number 12
I did not.
is a single replacement. Is magnesium more active than hydrogen?
Yes.
Yes, so that reaction occurs. This is the one where I did a little barking on the test tube, whoop, sound, you know, when we did that. Okay, so what are we gonna make?
Magnesium sulfate.
And back plus 2 and minus 2, so it's MgSO4 plus hydrogen gas.
So anytime hydrogen's released, will it make that bark sound?
We gotta light it,
Fire?
if you like it. Now, it's gotta be over a tube.
Yeah.
The sound is the hot air rushing down the tube, just like a wind instrument when you blow through a trumpet. You know, it's the air moving through the tube that makes the noise. And since when you light it, it gets super hot, the air expands real fast, and that's what makes the noise. All right, lithium and water. Replacement of hydrogen in the water by a very active metal, and it's gonna produce. This is where we have to remember that water is an HOH. So lithium is a metal. Even though it's 0 here, it wants to be positive. So is it going to be attracted to the positive hydrogen or the negative hydroxide? Negative hydroxide. Water doesn't break apart as a hydrogen and an oxygen. It always reacts as an H plus and an OH minus. So we're going to get LiOH plus 1 minus 1. And then hydrogen again is left over. This is the one we watched the video where when we got down to potassium and rubidium and cesium, the hydrogen caught on fire. And the cesium just blew the whole thing up. Now we have to balance it.
2 in front of everything except for the
Okay? And again, to me, it's just so much easier to see how things are going to react if you write water as an HOH rather than H2O.
So like technically, that's hydrogen hydroxide.
That's right. But, so this is a single replacement again. Magnesium carbonate, MgCO3. Metallic carbonates when heated. What common compound looks like CO3?
CO2.
CO2. So just take a CO2 away. We know that's a gas. Take CO2, that leaves just MgO, metallic oxide. That's an ionic compound, it's a solid. This is an ionic compound, would be a solid.
Wait, that's a decomposition, not, yeah.
All right, so now let's spend a little bit of time on number 15. What does it mean with limited oxygen?
The combustion is gonna be incomplete.
Combustion is going to be incomplete. You don't have enough oxygen to go around. So instead of making carbon dioxide, you're gonna make
Carbon monoxide.
carbon monoxide. Now, the reality is you'll make some carbon dioxide, some carbon monoxide, and some soot. Some pure carbon. Okay, so you get all three. When you have complete combustion, you only get CO2. When you have incomplete combustion, that's when you get the black smoke, that's when you get the carbon monoxide poisoning and all of those, so it's all three. And there's gonna always be a little bit of CO2 produced. Okay? 7 carbons, but if we were just to write this, we'll just put carbon monoxide on this one, because if you put everything in there, it'll never work out.
So we never put the plus 3 carbon. Like we never just put there's more carbon, like for the soot.
No, yeah, you just not.
You just leave.
Because the carbon's all gonna come from here still.
So,
Yeah, because your piston, believe it or not, is going, each piston, each cylinder is going up and down 25 times a second. Okay? So it's having to burn very quickly, but that's what the computers are doing now, is that they're adjusting and looking at the fuel to oxygen ratio, and you have those oxygen sensors in your exhaust that's saying, ooh, I got too much oxygen, too much fuel, and it is just constantly adjusting. Back in the day, we had carburetors, and the carburetor you had to adjust the carburetor to be getting the fuel and the air mixture just right. Even on your lawnmowers and stuff at home and gas blowers and stuff, you have that carburetor that, you know, gets messed up and it floods out, or, you know, it just gets wrong mixture.
That's frustrating stuff.
I know. I had mine set up for 2 years and none of it would start.
But that's like, when you get it just right, you know it.
Yeah, you
Yeah,
know.
you get it just right.
Okay,
right?
so C7, H16, so I have to put an 8, but that gives me 7 and 8 makes 15. What times 2 equals 15? 7.5, but we really don't want to have a fraction, so what do we have to do? Double everything. So put a 2 and a 14 and a 16. Now I have 14 and 16 makes 30. So I have to put a 15 there.
Those are the ones I hate that you have to write down and re-erase.
Yeah.
Oh,
So I got to create a pencil.
re-erase. That's not a word.
Share it.
All right, so that's the basics. Now let's look at the fun stuff.
Maybe that's why she gave me a 5.
That's what teachers say when stuff's about to get hard.
Yeah.
Combustion.
Yeah, this is a hydrocarbon combustion as well, yes. Okay. All right, so when you're doing these, let's go ahead and just write the normal molecular equation. So we're going to say sodium hydroxide reacts with nitric acid. Now we're going to assume that this is aqueous because that's the only way it can react. Nitric acid. Nitric acid came from which anion? Nitrate, which we know to be NO3 minus. So all acids, what's the positive thing? Hydrogen, so it's HNO3. So it's an acid-base neutralization reaction, and they're both going to be aqueous. In almost all double replacement reactions, I still missed. In almost all double replacement reactions, the two reactants are going to be aqueous because the ions have to be able to break apart from one another so they can rearrange. So what's this going to make? Sodium nitrate, Na+1, nitrate, NO3 minus 1, so it's just NaNO3 plus water, HOH. And this is a nitrate, so in terms of solubility, it's going to be aqueous. All right, now, when ionic compounds or acids dissolve in water, they dissociate, they break apart. So what are the two ions? Hey, listen. All compounds have two things only, a positive thing and a negative thing. It doesn't have two negatives and a positive. It doesn't have two positives and a negative. Things don't break down into 3, 4, 5 things. They dissociate into two things. Okay? The positive thing and the negative thing. So when I was looking at some of y'all's work that you turned in, you were breaking it, you guys broke them up into just about everything. Okay? So, what's my positive thing? What's my negative thing? Sodium's the positive, hydroxide's the negative. Now, total ionic. What is the definition of an ion?
Atom with a charge.
It's a charged particle. So what do you think you must write? The charge. You can't just say Na. You have to put the charge, because sodium metal, put that in the water, it's going to blow up. But sodium ion, the electron's already been transferred, so now it's got the noble gas configuration, so now it's much more stable, so when you put salt in your mouth, it doesn't blow up. So we're gonna get Na plus, and it's aqueous here, we're showing how it's actually gonna be in the water, plus OH minus. Excuse me. Aqueous. So this sodium hydroxide actually dissolves, and remember we saw the little video clip of the water coming in and surrounding the Na plus, then the water comes in and surrounds the OH minus, so they're completely separated, dissociated from one another. What's my positive thing and negative thing here?
Hydrogen and nitrogen.
Hydrogen and then the whole nitrate. So that's what it's going to break up into. H plus, aqueous, and NO3 minus, aqueous. A positive thing and a negative thing. Yeah.
Do we have to do the,
States on this one, yes. Aqueous, I don't know if that's where you're going.
no, balance it?
Yeah, but this one's balanced.
Yeah, but like, how would you do that? Like,
Well, we'll get it on this one. It'll come out. We'll see it on this one. You just multiply through. It distributes. The coefficient distributes to all the ions. So, okay. So since this is aqueous ionic, it's going to be dissociated. And what's my positive thing? What's my negative thing?
Sodium
Sodium
and then nitrate.
and then the nitrate. So it's going to be Na plus again, plus NO3 minus. But does water break apart?
No.
Solids, liquids, and gases always stay together. Only aqueous ionic break apart, and aqueous strong acids. Plus HOH, so we keep that together. So what two ions are exactly the same? Na plus is exactly the same. NO3 minus is exactly the same. Whatever your ions are in this soluble product, those are your spectators. So what's left? Well, OH minus from the base reacts with H plus from the acid to make neutral water. Acids neutralize bases, bases neutralize acids, because bases all have hydroxide, acids all have H plus, they come together to make water. The world is just beginning to make sense to y'all.
It still doesn't.
Hydrogen is the base.
Do what?
Is hydrogen the base?
No, the hydroxide always means the base, H plus is always the acid. Okay? So this is your acid, this is your base. Metallic hydroxide are all your bases. That's why alkali means base. So if something's alkaline, it's basic. So we have our alkali metals and our alkaline earth metals, because those are the ones that form the strongest bases.
So our batteries are base.
A lot of the dry cell, yeah, just like the C and D batteries and double A's, those are all, yeah, they have a base on the inside. We won't have time to talk about it, but in the original batteries were acid batteries, but for some reason with them, as soon as you start using them, the voltage begins decreasing as it runs out. And so little by little by little, and back in the day we had the Sony Walkman, the little cassette tape that you would wear on your hip when you go walking or something.
A weird little.
Yeah, big headphones. Okay, but you know, when you had a tape player, it had to go at a certain speed to make all the sound right. And then as the batteries got weaker and weaker, it started going slower and slower and slower. so it would just get all messed up, you know. But you guys don't even know. You guys got an A. All right.
Now you just click settings 0.75 speed.
Yeah. Now you just listen to me at 2 times speed. All right.
No, us give us our sound.
Are y'all positive and negative? Now, most of y'all did not get this didn't do this one very well, and the next one's even worse.
There's a,
No, I use dollars.
Whew, good news is we still have an hour left.
Yay.
I know this class is like
Never ending.
This is the longest. Okay. Solutions.
It's only been 50
Now this time they tell you, this helps, solutions of potassium fluoride and calcium nitrate are mixed. And since it's plural, that means they're both solutions. Solution doesn't mean liquid, solution means aqueous. A solution is a type of mixture. Mixture means two things, this plus water. So potassium fluoride, potassium is +1, fluoride is -1. So that's going to be aqueous. Calcium is what charge? +2, and nitrate -1, so I need two of them. And it too would be aqueous because of the solutions. So we're going to swap. So we're going to end up making what? Ca +2 and F -1, so CaF2 plus KNO3. K is +1, NO3 is -1. So even though there's a 2 here, we don't put the 2 over there. Now, if this reaction occurs, one of these has to be a precipitate. Which one would for sure be soluble? All alkali metals are soluble, all nitrates are soluble. So this is aqueous. This then has to be my solid. Now we have to balance this. 1 potassium, 2 fluorines. I have to have a 2. Gives me 2 potassiums. Gives me 2 nitrates, but looky there, 2 nitrates.
Wait, how do you know if it's solid?
Because the other one was aqueous. If it wasn't, then no reaction would occur. And we're just going to assume a reaction occurs. You could, that one's not up on our chart, so we wouldn't be able to look at it.
You know what happens when you start to assume.
I do know. It's happened many times. All right, so my total. Now again, y'all make corrections on yours because I know that you guys didn't do this right. I didn't hardly see a right one when I was skimming through. Now I did skim through quickly. What's my positive thing? What's my negative thing?
Positive is K.
But this 2 is going to distribute to both of them. So if I have 2 KFs, okay, let's go elementary math here. Okay, come on, Bree. I know. If I have 2 KFs, how many Ks and how many Fs am I going to get? 2 Ks and 2 Fs. The 2 is going to distribute. So I'm going to get 2 K pluses plus 2 F minuses. Jackson, I think that was your question. Okay? Now again, if I have calcium nitrate bonded to another nitrate, and they're all going to break apart, this is a minus, and a 2 plus, what's it going to break apart into?
1 calcium and 2 nitrates.
1 calcium and 2 nitrates. So this subscript, that if I keep it as a subscript, that would say that the nitrate is chemically bonded to another nitrate, but 2 negatives are not going to come together. So the subscript becomes a coefficient. It's going to break apart into the positive thing and the negative thing. So however many of the negative things you have, that becomes the coefficient. So solid is going to stay together. So what am I going to get here?
2 potassiums and 2 nitrates.
2 K pluses and 2 NO3 minuses. So what are my spectators?
Potassium and nitrate.
Potassium and nitrate. The thing that's aqueous over here is always going to be your spectators. So my net ionic equation is 2F minus. This is really what's happening is the F minus and the Ca2 plus are getting together and making CaF2 solid. The other potassiums and nitrates, they're just there. Not changing at all. All right? Total net ionic equation is what gives students the hardest time year after year after year. Okay? So we're going to practice a couple more until we get comfortable with it. Then we're going to move on. Okay, any questions on this? Are we seeing how we distribute? Are we seeing how the subscripts come in? Okay? All right. This is your time to practice now. We work hard in class so we don't have to work hard out of class. Work hard in school so we don't have to work hard at home. Turn the sheet over.
Mr. Hobbs, with number 15 on that, C7H16, that's a combustion pipe.
Yeah,
right?
HC. I wrote that in at the end. So what I want you to do, now it says on the bottom there where it says describe in words the following chemical reactions. I want you instead to do total and net ionic equation for number 1 right now. Just on this sheet right here on the front. Okay, number 1, the whole equation's given to you. Just break it down into the total and net ionic equations for number 1. Y'all, the balancing on this sheet, I've been doing this for years. But that should be 6 water, shouldn't it? You know, number 1? Yeah, it should be 6 waters, not 3.
Oh,
Because
shoot,
there's
no
6
wonder I was confused.
hydrogens
I've done
and
the wrong
6
number 1.
hydroxides.
6 hydrogens and 6 hydroxides, so we need, 6.
That makes 1 year sense.
I know, and I don't know how, over all these years, I have never seen that before and corrected it.
No, I was just doing the wrong number 1, that's all.
Oh, well, that's a problem too.
We're doing total and net, right?
Yes. if you're struggling at all, ask a friend, phone a friend, as they say, who wants to be a millionaire. Is it hot in here or is it just me?
It's not cold.
It's not cold, but I don't think it's hot.
It says it's 71, but it feels 74-ish.
Always cold.
All
You know
have
the
sweatshirts on.
stretchy
Sweatshirts are less of a weather type thing and more of a comfort.
Yeah, Zinc Hydroxide.
Okay. What's zinc hydroxide going to break up into? Three zincs, and what's the charge going to be? 2 plus. You don't guess. You just go look on the periodic table. You find zinc. There's a number 2 right above the symbol. It's going to be +2. Okay? You just got to look. Plus, you could, the other way you can know is, again, the reverse crisscross. That 2 probably came from +2. Hydroxide is -1. So how many hydroxides am I going to get? 6 hydroxides. Does everybody see that? 6 hydroxides, because each one has 2 and you got 3 of them, so you're going to have 6 hydroxide. Now this one, what are we going to get? 6 H pluses.
And 2, what is P?
Phosphates.
Phosphate.
You're not going to get P's and O's, you're going to get PO4s. Okay? Now, for y'all right now, that's the way I want you to break it up. But the reality is that we have 6 strong acids. Okay, they're the top 6 on that chart over there. Those are the only ones considered strong. On the far right, the chart over here, relative strengths of acids and bases. Okay, the top 6, HClO4, HI, HBr, HCl, HNO3, H2SO4. Those are strong acids, which means when you put them into water, they break apart 100%. Every other acid on the chart is considered a weak acid, including phosphoric acid. So technically, now again, as soon as I saw it, I signed this, I saw this, and I said, oh, but I didn't feel like changing at that point. Only strong acids ionize. Weak acids ionize just a small extent, so the majority of them are going to be together. So technically, we should keep this one together as just H3PO4. Okay? Only strong acids break apart. Now, I'm not going to hold you to that. Take AP chemistry, I'll hold you to it. But today, no. But so you write it this way because that's what all you knew at that point, which is 100% right. But the reality is that a weak acid we're going to put and keep it together. Only strong acids are going to ionize, break apart. All right. Just a little. So what's this going to make?
3 zincs, 2 phosphate.
3 Zn 2 pluses plus 2 PO4 3 minuses plus 6 waters together. Water never breaks apart. So do I have any spectators? 3 zincs and 2 PO4s. And we end up having 6 OH minuses plus 6 H pluses going to 6 H2Os or HOHs. Now you could technically, because it's 6, 6, and 6, get rid of those. Because you always want to reduce the coefficients if possible, the smallest ratio. Do we get that one right? Okay, let's do one more. Over here. is due tomorrow. Is it due today? I thought I said Friday, but I can't remember.
Google Classroom doesn't say, but yeah.
I have no idea.
We'll say that the lab is due tomorrow. Whether or not it makes it onto this 9 weeks, touch and go. Oh, crud. Shoot. I messed up this time. I was supposed to bring this back. So, yeah, so seventh period. Huh?
Iron hydroxide the solid.
Okay. Iron, this one is gonna be your solid, that's gonna be your aqueous, that'll be your solid. Okay, and again, you come back up here and you look, most hydroxides, only those few hydroxides are soluble, most are insoluble. Most hydroxides do not dissolve. Those are gonna be your precipitates. But again, know the one for sure that's aqueous, the other one's gonna be your solid. Try not to envision the lunch line right now as they're giving away all the good
That's
food.
messed up, Mr.
By the time you get there, 1:35, there's basically nothing left.
We could go to Hobbs. I got a question.
That's gonna be a precipitate because, again, you're making NaCl. So all alkaline metals are soluble. The other one has to be precipitate.
So you take a solid,
Yeah.
How would you do number 2 on the, this one? On the other side? Cause it has like the O2. You wouldn't do.
You don't do it total or net with that. Because nothing's gonna break apart because you have solid, solid, and gas, so that nothing breaks apart.
So, how come you can't just let us go once later?
So I'm a rule follower.
No,
Yeah, famous last words, we won't tell, I promise.
How come they don't have science go
Yeah.
first? You should have science go first.
See, but then everybody that's in history right now thinks they should make history go first.
We're kind of big.
It's supposed to be during third period anyways, so.
Thursday's always been late lunch.
But like normally it would be during third period and then it wouldn't be as.
There.
If they start at 8:30, that means you'll be eating lunch at 2. If next year, like they say they're doing.
Why would they, that makes no sense, they're gonna make class 20, or day 25 minutes longer, but start 15 minutes later.
Is iron chloride? Oh, solution. Clay.
They're adding 25 minutes to the school day, but starting 15 minutes later, so they're adding 10 minutes total.
Can we get some more off? Because we're stupid.
Got it out of a book.
I don't know. Central office just kind of figured out a way to screw things up. I guarantee it's not a Spain Park decision, that's a Hoover City school decision. Yep. Okay, so first off, you gotta make sure that you have your molecular and your normal equation right. We get it? No? You got a positive thing and you have a negative thing. What's the positive thing? What's the negative thing?
Iron.
Iron is the positive. What's the negative ion? Is it a Cl3 ion? It's the chloride, it's a Cl minus ion, right? Chloride forms a Cl minus 1, not a Cl3 minus. It's not a polyatomic ion. So it's just going to be that. So we're going to get Fe 3 plus and 3 Cl minuses. Because basically, I mean, you have an Fe 3 plus with a Cl minus, a Cl minus, and a Cl minus is just kind of all attached to it. And they're all just going to break apart and make the 3 Cl minuses. You got to know, what's my ion? The halogens are all going to be just F minus 1, Cl minus 1, Br minus 1, I minus 1. Okay? You're not going to have di and tri, O2, you know, O3, 2 minus or anything like that. Plus, what am I going to get here?
3 Na plus,
3 Na pluses,
3 OH minus.
3 OH minuses. Right? What about this one? Does this stay together or break apart?
Stay together.
Why? It's a solid. What's the only ones that break apart?
Aqueous.
Aqueous. Aqueous ionic and strong acids. Then we're going to get 3 Na pluses plus 3 Cl minuses. So again, this is my aqueous one, so that is going to be my spectators. So my net is going to be Fe 3 plus 3 OH minus going to Fe OH3 solid. Okay, so where is there still some confusion? Anywhere?
I kind of don't understand like the coefficient, like the numbers, really. Like whenever you write it out front, as opposed to.
Okay. Being as far as in the net, total in net,
Yes.
okay? Because we have to know what the ions are. So when it's like a phosphate, PO4 subscript, that's part of the polyatomic ion. So I only have one PO4. Okay? So that's why we got to be familiar with these polyatomic ions. The monatomic ions, if it's just chloride, fluoride, oxide, sulfide, that's just going to be this. And so if you have a Br, you know, like on this one, FeCl3, well, the ion is a Cl minus 1 ion. That means I'm going to have 3 of those. So the way you know is you just have to be familiar with your ions.
So if it was like iron 2 chloride, it would keep the substrate.
No, because it's only going to be diatomic when it's chlorine gas, not when it's dissolved. Okay? So you're not making chlorine gas when it breaks apart. You're going to get 2 Cl minuses still. The 2 negatives are not going to come together. So if you put a subscript 2, that would be the 2 chloride ions bonded together, and that's not going to happen. What else? Work it out. Okay, I want to do one more times. I'll make sure I have enough time to do this stoichiometry thing. Let's look at a single replacement, total and net ionic equation for single replacement. Let's look at this magnesium plus sulfuric acid. Okay? So if I'm gonna write my total ionic equation for this, it's gonna be magnesium solid. Now this is a strong acid, so it's gonna break up into what?
Multiple H2s and H2.
Two H.
Not H2,
Two H.
two H's, because what's the ion? H plus. It's not an H2 ion. We're not making hydrogen gas here. Hydrogen gas over there, but this is two H pluses attached to the SO4 minus 2. A positive thing and a negative thing. Two H pluses. Plus an SO4 2 minus. That's my sulfate ion. That's my polyatomic ion. It acts as one thing. So I don't get 4 SOs or any there. SO4 is my polyatomic ion. It's going to break apart into Mg2 plus, aqueous, SO4 2 minus, aqueous, but hydrogen stays together because it's a gas. When the hydrogens, oxygens, chlorines, fluorines are combined in a compound, they're not diatomic. It's only when it's chlorine gas, hydrogen gas, oxygen gas, either as a reactant or a product. Do you do the O2, F2, Cl2? So what are my spectators here?
SO4.
Just the SO4, right? So we end up with magnesium solid, which has 0 charge. In other words, the electrons and protons equal, plus 2H plus, which doesn't have any electrons, and it goes to Mg2 plus H2 gas. So the whole reaction, when you put this in and we saw the bubbles given off and all the hydrogen gas and it got real hot, all of that is the result of hydrogen stealing electrons from the magnesium. Hydrogen has a greater attraction for electrons than magnesium does. As a result, it steals the electrons, magnesium becomes the ion, and it dissolves, and the hydrogen gas bubbles out. And then for fun, we light it. Okay? And when we light it, it makes water, and oxygen steals the electrons right back from it. Okay? We need to be able to do it. You're going to have a quiz tomorrow. So if you need to, just kind of go keep practicing tonight.
So, remember the iron that stayed solid? Does that have, as a,
Here and here.
as a previous,
Yeah.
like when it stayed solid?
It's just, yeah, I mean, again, it's solid. We're representing how it is. So only aqueous is going to break apart. So this means it's going to be that solid forming at the bottom, just collecting as a precipitate. And this is going to stay in solution. I think that was your
Wait,
question.
how do you know it's solid?
This one? Because this one was aqueous. Okay? One of them has to be a solid. Something's got to be a solid, liquid, or a gas. Otherwise, there's no reaction. The second way we know is you turn around and you look at the hydroxides, and only group 1 and barium and strontium are group 2 are soluble. Everything else is insoluble, all hydroxide. So that's a second way to know. But generally, just know our big 3, this is an alkali metal, so it's aqueous. So the other one has to be the precipitate. Okay, so quiz tomorrow. We're gonna learn how to make s'mores. Oops.
Well, that's kind of cool. Mr. House, we should do that one day. Just like use the lab money, buy s'mores, we go make them in the lab.